today we're going to start by talking about like what is a polynomial function. So polynomial functions are going to be functions where we have a number as an exponent, an integer value specifically, all right, and they can go up in a lot of degrees. So quadratic functions, what we dealt with a lot last year, are degree 2 polynomial functions, right? And we're going to look at some of those types of things today. So first we'll start with the definition of a monomial. So a monomial is an expression that is a number, or it's a variable, or it's the product of a number and a variable. So some examples of monomials are like just the number 3, that would be a monomial. Or you could have x by itself, that's a monomial because it's a variable. Or 5 times y, that would be a monomial. So just like one term all by itself. That's what a monomial is. And then a polynomial is a monomial or a sum of monomials. Okay? So it means we're just adding a bunch of monomials together. That's where a polynomial comes from. All right? So a polynomial function is going to be typically in this form, and this is what's considered standard form of a polynomial. Of a polynomial function. And it looks really intimidating because of the way it's written right now, but once we break it down, hopefully it won't be that bad. So for example, we start with this a sub n, which is just a placeholder, and what that really means, a sub n, that's the leading coefficient. So whenever we're talking about a polynomial function, we're going to be talking about the leading coefficient. And the leading coefficient has some rules. Like, for example, it has to be a real number. So it can't be and it can't be 0. So the leading coefficient cannot be 0 and it has to be a real number. It can't be an imaginary number, which we'll talk about imaginary numbers briefly, but we're really not going to go too far into them in this course. All right. And then we'll have the leading coefficient times x to the n power. And n, all right, is the degree of the polynomial. So that if it's written in standard form, you can always identify the degree of the polynomial pretty quickly. N is the largest positive integer. That's the largest positive integer value exponent. Okay. And when we're talking about these polynomial functions, this is important to note. We can only have whole numbers for exponents. All right. So what we talked about last unit with logarithms is exponents could be negative numbers, and they could be fractions. But right now we're going to say no fractions, no negatives, which is key. That's going to save us some pain, some headaches. No fractions, no negatives for exponents in this polynomials unit. Otherwise, it won't be considered a polynomial function. So what I mean by that is like x to the -3 power, x to the 1/2 power. We're not going to see anything like that this time around. Okay? No negatives, no fractions. All right, the last value I want to point out to you guys is the very last term. This is the constant term, and it's a sub 0, which we talked about, like that being initial value when we worked on those real world problems. But this is also the constant term. Let's do a sub 0 the constant term. All right, the C value from quadratics. All right, so remember, and what I mean by the C value is when we had standard form of a quadratic, we had ax squared plus bx plus c. C is that constant term. Another way you think about it is whatever the polynomial function is, this is also the y-intercept. Be 0, comma, a sub 0, whatever that value is, would be your y-intercept of the function. All right, so that's the general standard form, and we're going to talk about what all the other numbers in the middle kind of look like too. But I think it's going to be very helpful just to just see a bunch of examples of this, and then hopefully this general form will start making sense, because it looks really scary right now because it's got this an x to the n and then an minus 1 x to the n minus 1 and then this dot dot dot. So I can see why that would be a little intimidating. But it's not too bad once we actually see it. Okay? So a polynomial function is going to be in standard form. Let's do a different color here. It's going to be in standard form if its terms are written in descending order. Of exponents. From left to right. Descending order of exponents from left to right. And we'll do a couple examples of that on this table below, what I mean by that. So first, if we start with a constant term, that's going to be a degree 0. And typically the constant term would just be like a sub 0. An example of that would just be any number, like 4. There's a constant term. Okay. A linear function is one we're used to dealing with. That's always of the form like y equals mx plus b. Except we're not going to call it mx plus b today. We're going to call it a sub 1 x plus a sub 0. We're going to try and keep this form going where it's like there's one term a sub 1 and then the next term is a sub 0. This might look like something like 3x plus 5. I'm just making up these numbers on the right in the example column. All right. Something to note about a linear function, it's never written down, but it's implied that this is technically x to the first power. Implied x to the first power.
So for linear, it's a1 x and then exponent 1.
Yes, exactly. But we don't need to write the exponent. We can just imply that there's an exponent there. Exactly right though.
Okay.
Yeah. Quadratics, we've seen this before. Ax squared plus bx plus c. Except now we're just going to write it as a sub 2 x squared plus a sub 1 x plus a sub 0. What I want you to notice is, remember I called it descending order. It means they're going from bigger numbers to smaller numbers. So what we'll see is like, hey, this is a sub 2, a sub 1, a sub 0. We'll notice that those numbers are going down by 1 each time as we go from left to right. The other thing that's going down each time is the exponents. There's x squared, x to the first power, which we didn't write down. And then technically, there'd be an x to the 0 power over here. But you don't need to write x to the 0 power because that's just a 1. All right, so an example of this would be negative 2x squared minus 5x plus 7. All right, and again, I just made up those numbers for the quadratic function. As we keep moving, like a cubic function, degree 3, that's going to be a sub 3x cubed plus a sub 2x squared plus a sub 1 times x plus a sub 0. And hopefully this down here now, as we see a couple more examples, hopefully that's starting to make sense with what's going on up here, because it was a sub n, and like let's say the n was 3, then this would be 3 minus 1, so that's a sub 2. And then this was x cubed, and this was x cubed minus 1, which is x squared. So that's what's going on with this polynomial function standard form up top. All right, and that's how it relates to the common polynomial functions we're looking at below. An example of a cubic function, we could have like x cubed minus 6x squared plus 2. And we don't have an a1 sub x term because we could just say x equals 0 in that case. Or we could say a1 equals 0, I mean. Okay, so that's a good example for that type of problem. All right, last one, a quartic, just keeps building. Now it would be a1 x to the fourth, or I'm sorry, a4 x to the fourth, plus a sub 3 x cubed, plus a sub 2 x squared, plus a sub 1 x to the first, plus a sub 0. That's an example of a quartic function, fourth degree polynomial. And then we have 2x to the fourth minus x cubed plus x squared plus 3x minus 9. That's an example of what a fourth degree polynomial would look like in standard form, descending order. All right, so that's just an example. If I asked you to identify the leading coefficient of each of these, like let's do that in purple. So we'll say leading coefficient, because it's important to identify that leading coefficient. It would be 4, 3, negative 2. So it'd be 4, 3, negative 2. Do you guys see that? It's just whatever number is in the very front. If there's not a number written, like it's just x cubed there, then the leading coefficient is positive 1. And then the last one, the leading coefficient would be a positive 2. That would be the leading coefficient of each of those. So that's how you'd identify the leading coefficient. That's what this part was asking. And then if I asked you to identify the constant term, it would be whatever the very last number is without an x value associated with it. So if I said constant term, oops. The constant term for this one would technically be a 4 as well. For the second one, it'd be a 5, then a 7, a 2, and a -9. That would be our constant terms, whatever the last values are that don't have an x associated with them. And they take the sign with them too. Okay? That's the idea for what I was talking about in the 3 boxes up above. So from any polynomial function, just by looking at it, we got to get good at identifying the leading coefficient, the constant term, and also what's the degree of the polynomial, which is by looking at the very first exponent, if it's in standard form. Those are the 3 things we're going to be practicing in just a second here. First though, what would a 5th degree polynomial look like? What I want you guys to do is write down a standard form 5th degree polynomial, like what we were doing up here, standard form, and then write down an example of it. Okay, so go ahead and do that now for a 5th degree polynomial. Take a minute to do that. All right, I went ahead and wrote down the 5th degree polynomial here. So it'd be a sub 5 x to the 5th plus a sub 4 x to the 4th plus a sub 3 x to the 3rd plus a sub 2 x squared plus a sub 1 x plus a sub 0. Yeah, question.
Yeah. How did you get the examples exactly?
I just made up the numbers. You can make up you can make up whatever you want for an example. So,
okay.
Yeah.
So you plug in whatever a is or something.
You plug in whatever values you want. Like, hey, if I wanted to say an example here, y equals 17x to the 5th. That'd be an example of a 5th degree polynomial with the first term. And okay, you make up whatever number you want, minus 5x to the 4th plus 3x cubed minus or plus 12x squared. Any numbers you want to make up, you can make up.
Okay.
All right. Minus 5x plus 6. There we go. There's an example of a 5th degree polynomial with numbers made up for every single term along the way. Okay. Okay, now I've got 4 examples I want you guys to try. We're going to decide whether the function is a polynomial function, so we're going to write yes or no. Polynomial function means it has to meet the criteria that I listed in the 3 boxes at the very top of the worksheet. So you just say, yes, it's a polynomial, or no, it's not a polynomial. So for example, number 1, we'll just do a little dot. And I see, all right, it starts with an x to the 4th. It's got an x squared and then an x to the 0 power technically here. So yes, it's a polynomial function because all of the exponents are positive numbers and they're all integer values. So that's what I need to do to decide if it's a polynomial function.
Wait, the last one would have a 3x0?
Yeah, if there's no exponent written, it would technically be an x to the 0 power because x to the 0 power is just 1.
Okay.
So that's what the constant term is. So like up here, this would technically be a sub 0 x to the 0. But we don't need to write x to the 0 because it's just 1. Does that make sense?
Yeah, that makes more sense.
Yeah, so that's why it goes x to the 5th, 4th, 3rd, 2nd, 1st, x to the 0. It's just counting down from 5 to 0 all the way across. Okay? So this example, it goes x to the 4th, x squared, and then x to the 0, but it would be a polynomial function because all the exponents are positive, and they're all, whoops, something froze. Oh, it's back. Okay. They're all positive, and they are all integer values. Then if yes, write it in standard form. So this one right here, we need to write it in standard form, which is descending order, which it turns out it's already in standard form, so I'm just going to write it down again. I don't need to reorder it at all. Okay, which is kind of nice for that one. And then if yes, state its degree as odd or even. This last part, state the degree as odd or even. And what that means is you need to look at the leading coefficient 4 and say, not the leading coefficient, sorry, the leading exponent. And it's a 4 and say, is that an even number or an odd number? That's an even number. And then we're going to identify the leading coefficient as well. And the leading coefficient here would be whatever number is in front of the x. In this case, it's a 1. So even degree, and then leading coefficient is the number 1. That's how I'd want to do these types of problems. Just do a bullet point for each one. All right. If it's not a polynomial function, we're going to explain why. Okay, what makes it not a polynomial function? So go ahead and try problems 2, 3, and 4 now. Take a few minutes to work on those 3 problems. Let me know if you have any questions. And we'll take a look at them together in a couple of minutes here. All right, so that covers the last 4 examples there. The last thing I want to talk about today is odd degree versus even degree polynomials. There's a reason we want to identify odd degree versus even, which is one of the things I asked you to do on these 4 problems. And that's because if we look at odd degree polynomials, like this first one, x to the first power. Another odd degree polynomial would be x to the third. Another one would be x to the fifth. And then even degree polynomials like x squared, x to the fourth, x to the sixth. You might notice there's something different about the graphs for odd versus even degree polynomials, right? Something different about the graphs for odd versus even degree polynomials. What do we notice that's different about these two? I'm going to put arrows on these to show that these go on forever in all directions. Where do the even degree polynomials always end up? They're pointing...
They go up.
Up in both directions, right? And the odd degrees, they're going in opposite directions. One side's going down, the other side's going up. That's going to be true for all of these functions. So I'm going to throw a definition out at you guys right now. There's something called end behavior, which I feel like I might have mentioned briefly in passing, but we're really going to cover it this unit. End behavior, this is like the function's behavior at its extremes. So the function's behavior at its left and right extremes. So odd degree polynomials have end behaviors that go in opposite directions. That means on any odd degree polynomial, if you're saying, hey, the left side's going up, then the right side has to be going down. They're going in opposite directions. Okay? And that means, hey, if the left side of the graph is going down, that means the right side of the graph has to be going up, opposite directions. That's what I mean by that. We're going to get a lot of practice with this over the next few class periods. Even degree polynomials have end behaviors that go the same direction. So today, all we see on the even degrees, both sides are going up. Left side's going up, right side's going up. What we're going to start looking at in class is we'll see, hey, some even degree polynomials have both going down, which is fine. Some have them both going up, some of them both going down, but they're always going to be going in the same direction. Okay? So that's the key for what's called end behavior, and we're going to practice that. Basically looking at the extremes of the graph. What happens as the function goes to the left side forever? What happens as the function goes to the right side forever? Okay? That's the idea for end behavior.